No, we still cannot hear you. Hello, Prof. Prof. Chen. Hello, Prof. Hello, Prof. Chen. Hello, Prof.
Apologize, Professor Chen. We see you speaking, but we could not hear you. Professor Chen, apologize for the interruption, but we still could not hear you. Perhaps you could leave the meeting room and back again to reset the setting of the microphone.
Yeah, sometime it's happened. A technical, yeah. Yesterday it happened also with the speaker from Germany. I hope that yeah, it will be okay. It's from with Professor Cheng. Has it enter again? Okay. Hello, Prof. Hello, Prof. Cheng. So yesterday, actually, we can offer also the presentation from us, and then he can just speak. But the problem with the audio, actually, yes, because Professor Chen already sent also the presentation. Okay. Hello, Prof. DongFeng.
Yes, can you hear me now?
Oh yeah, no, clear. Yeah. So you want to share by your side, or you want us to? I think you can share your screen. No, it's
Yeah,
clear.
I will share now. Sorry.
Yes. Okay, no problem.
Okay. Now, can you see my screen now? I will make it the full screen. It's a full screen now.
Yes. Yeah.
Not
Not yet. Not yet.
It's
You can
now full
put
screen,
the-
right?
Oh, yes, perfect. Professor.
Can I start?
Yes, Professor, please start.
Thank you very
Thank you.
much. I would like to thank our organizer, especially my friend and my colleague, Professor Evie. Thank you very much. Giving me this opportunity. Actually, I visited Indonesia in 1993, almost about 30 years. So that's my honor here to give my topic, which title is Investigation on Energy and Environmental Materials by using CARR Neutron Facility. CARR is also called China Advanced Research Reactor. From our last speaker, I'm very pleased to see we have a lot of resources on energy in Indonesia. Actually, in my talk, I would also like to mention about some how to use these resources like nickel to make a better clean energy, like a battery. And in China, the government also pushed a lot of clean energy projects like solar, like tide, like other energy resources. So let me first introduce a little bit about our institute. China Advanced Research Reactor located in CIAE, also called China Institute of Atomic Energy. From this slide, you can also see there are several reactors. Actually, it totally about 13 reactor like big facility. Some of them is used for the clean energy. Some of them is used for the science and application like this CARR project. From this CARR, you can see from this picture, we have the cooling tower here. We also have a reactor building here. And behind is a very famous mountain, so-called Yanshan Mountain. It's located about 40 kilometers from the center of the capital, the downtown area. And also they have a new airport, so-called Beijing Daxing Airport. It is about 40 minutes from the airport to my place. So if you visit Beijing, you will feel much more convenient now. We also have the other airport located here. That is a far east part of the capital. It will spend about 80 minutes. So both this airport can come to my institute. So this institute already built about 70 years. We just passed the anniversary for 70 years birthday. And also called the cradle or birthplace of Chinese nuclear industry and birthplace of China nuclear science and technology. Now we have more than 4,000 staffs. Actually, it's 4,217 staffs. We focus not only on basic science and also focus on the application and the nuclear related R&D. From today's presentation, I will spend more time on the battery related research. You know, Professor Avi Cartini spent a lot of time. We work together to push this direction. Cartini, professor, she linked with the battery and the neutron. I think it is a very promising direction. In China, we also spend a lot of time, a lot of resources, use neutron as a probe. to study lithium-based battery. And now I'll introduce a little bit about the sodium-based battery. And we also use some other technology, not only neutron diffraction and scattering. We also use neutron activation analysis and neutron imaging for hazel control, small control, and also for fuel cell. And if we still have time, I was a little bit introduced about neutron facility. That's also so-called instrumentation. Maybe you already know the Professor Avi Katini's research. Actually, we use neutron as a probe studies kind of battery materials. If you use neutron, it's kind of complementary tool with X-ray and synchrotron source. And that is a very powerful tool for material characterization because its property is very sensitive to hydrogen, the carbon, the nitrogen, and we can distinct also neighbor element like the iron, cobalt, nickel, and copper, titanium, and so on. And neutron also the deep penetration probability make it very powerful tools to study large bulk samples. So you can study even the real batteries by neutron, and also easy to use very complicated sample environment for in situ study in battery. So as we know, capacity, let me see, yeah, here. We will use three techniques from my talk to solve different kind of problems. First, we use neutron imaging. It's a very direct way to study the materials. The neutron is quite different with some other source like the light source. And we also use neutron scattering, including neutron diffraction to study the structure and dynamic of the materials. And finally, I will also introduce about neutron activation analysis. Let me show you the first. I will introduce about battery materials. As we know, everybody know the lithium battery is kind of popular in the global market, but literally spend a huge amount of resources on the sodium ion based battery, so-called NIBs, NIBS. It have attracted huge attention due to a high abundance and easy accessibility of sodium resources. Now, it is very useful in China, like the energy storage method. For large-scale energy storage due to the low cost compared with lithium battery. Sodium ion battery consists of the positive electrode, negative electrode, electrolyte, etc. Very similar to lithium ion battery. When charging, sodium ion move from the positive electrode to the negative electrode inside the battery. At the same time, the electron flow to the negative electrode in the external circuit. For discharge, the process is opposite. As we all know, capacity and cycle life are most two important factors for a good battery. The capacity of a battery is determined by how many sodium ions can be removed from the positive electrode. And the cycling stability or cycling life of the battery is mainly determined by the structure stability of the positive electrode during charge and discharge process. So how to design the better positive electrode battery is a material is very most important for the battery. So that's why I introduced why we use the neutron to study battery. The neutron has a lot of very interest and a good gift to study battery material. So let's take a look about this structure of the battery. One of the most promising positive electron materials is a layered oxide. You can say layer by layer because of their good performance and easy preparation process. Here we show the crystal structure of layered oxide. You can see here we have a sodium. The yellow color is sodium ions are sandwiched between the transition metal. We label it as a TM, transition metal layer, to form a layered structure along the Z-axis. for crystal structure, C is on this direction. The crystal structure of layered oxide is similar to that of the so-called Jenga, as shown in the right picture. Imagine that every other wood block layer stands for the sodium ion layer, and the rest stand for the transition metal layer. We want to remove the wood blocks as many as possible, but we also want to keep the Jenga stable to avoid collapsing. So that is very similar to the sodium ion batteries. So we also want to remove as many as possible sodium ion from the positive electrode while keeping the positive electrode stable. So now the question is how to design the composition and structure of layer oxide in order to have better performance, and what is the mechanism behind. Actually, we have tried 3 studies. The first one is we designed the composition of the transition metal layer, the first layer. Secondly, we are little talking about designing the composition of the sodium layer. Third, we will design the composition of both transition metal layer and sodium layer. So that is our first work. The first work is design the composition of a transition metal layer, considering the different role of different elements. So here is our roadmap. Firstly, for low cost, we choose manganese and iron because they all rich-for and environmentally friendly. Secondly, we use nickel and copper to replace some iron because they can provide enough electrons to help achieve high capacity. Thirdly, we add some titanium to stabilize the structure because titanium doesn't participate in the redox reaction. So we designed and prepared a positive electrode material with 5 elements: sodium, nickel, copper, iron, manganese, titanium, and oxygen. We hope this material will show a much better good performance. Here is our final result. With the deep allowed how to prepare our sample, we use muffle furnace, we use Muller, we squeeze the sample, we spend about 20 hours to make the sample. Where our students, we have a Professor Sun Kat's group and Dr. Guo Hao. They collaborate with our Institute of Physics belong to Chinese Academy of Science. We also collaborate a lot of collaborators from graduate school of Chinese Academy of Science. Actually, we work a lot with our universities and Chinese Academy of Science colleagues. And results shown in the table, you can see that our design 5 component materials show better cycling stability than some reported good positive electrode materials, and also relatively high capacity. Here, I would not introduce more about this. We have this measurement capability, but I will not go into detail, but I will show some neutron-related skills. Here is a neutron powder diffraction technology. We close collaborate with the spallation source, reactor source, and we also collaborate with our AONSA colleagues. This picture comes from Australia, the ASTO reactor, and it shows us very good resolution. And you can also find that at high angle is much better data and a very good resolution compared with X-ray. That is very sensitive to light element like the oxygen and the sodium. And it also can distinguish the near neighbor like the transition metal. Since we have nickel, we have iron, we have titanium, also have manganese and copper. They also have very high Q range, so the high angle resolution is very good. We carry out our neutron powder diffractometer to study the structure and composition of our samples. The structure is determined to be like O3 type oxide without any impurity. So the sample quality is perfect, so-called oxyhedral 3. And the refined composition is also single phase. It's consistent with our design. So that's a perfect matching. That is sodium 0.9 and nickel 0.284, copper 0.099, iron 0.13, and manganese 0.306, titanium 0.154, oxygen 2.206. The design, I think it is very good matching. Let's see this. It also carried out this charge and discharge with figure by X-ray. That so-called in situ XRD measurement will investigate the structure change during the charge and the discharge process. The result is shown here. During the charge process 0003, I mean this one, you can see from figure, that is a shift from a low angle indicating a solid solution reaction. Then its peak disappears, but a new peak corresponding to prismatic P3, so-called P3 phase appears. We can see the phase transition, and the upon discharge, the structure change back again. So we can see the process is highly reversible. This means the material is stable during the charge and discharge. Let's see the next slide. Let's use the Jenga again. So during the charge and discharge, there is no other phases like O.3 or P.3 phase, only P3 phase is founded. It is believed that the appearance of O.3 and P.3 distortion structure is very harmful for the cycling stability. Even they can make the collapse. So the highly reversible O3 to P3 phase transition is responsible for cycling stability. Let's go to, you can also see our publication by Dr. Guo Hao. And also we have a collaborator, Hu Yongsheng, professor from the Institute of Physics, come from China Academy of Science, also Professor Sun Kai, and myself also joined this project. And also have scientists from AONSA, so-called the maximum additive. Let's see the next page. Secondly, we designed the sodium layer. That's our second work. Here we use another kind of structure, so-called the P2 type structure oxide, to design the sodium layer. It is well known the prismatic 2-type layered oxide are typically sodium deficient. That means sodium ions are not saturated in the structure. As shown in the figure, this system have several intrinsic sodium vacancy in the crystal structure. Therefore, we could think about doping some other element to those sodium vacancies to improve the performance of the battery. So we tried doping magnesium to the vacancies. We think the doped magnesium ions may serve as a pillar to stabilize the crystal structure upon the extraction of sodium ion, because the manganese iron are electrochemically inactive and they do not move during charge and discharge. Let's see this slide. Now we use the CARR high intensity neutron diffractometer. We also call this diffractometer as the Peking University diffractometer, because we co-built this diffractometer. It is quite productive per year. It can make more than 300 to 500 samples. So now we use this Peking University diffractometer to study the location of the manganese ions. And we found that the doped manganese ion occupy the vacancy of sodium layer, not the transition metal layer. And most of the magnesium enter the vacancies of H-shared sodium sites rather than the phase-shared sodium site. This may be due to the much higher stability of the H-shared sodium site than the phase-shared sodium site. So according to the electrochemical performance test, we can also do this in our lab. The capacity at high current densities improve significantly. This can be ascribed to the enlarged space sodium ion diffusion due to mechanisms in the vacancy in sodium ion layer. Second conclusion is the cycling stability also increased a lot, as shown in the right figure. This is due to the manganese ion in the sodium side serving as a pillars or spiker to stabilize the crystal structure during charge and discharge. Thirdly, we also designed the sodium and a transition matter TM layer at the same time. In our last study, we have doped manganese iron to some intrinsic sodium vacancy in P2 type oxide cathode. Here we try to dope lithium ion into both sodium vacancies in the sodium layer and TM layer simultaneously. We choose the classic P2 sodium 2/3, nickel 1/3, manganese 2/3 oxide 2 as a great model material and realize our design. Because NNO suffers from a lot of problems such as the serious P2O2 phase transition, so-called transformation at high voltage. The voltage from 4.1 to 4.2 volts, different ordering process, including sodium vacancy ordering in sodium layer, the cation ordering and even charge ordering in the transition metal layer. It has been proven that this issue can significantly degrade the voltage curves, capacity, decay, and cycling stability. Because neutron is a very sensitive to lithium element, so we use HRPD, which is a high resolution powder diffractor. It is made in CAE and also China at CARR, China Advanced Reactor, to analysis the lithium location. So this high resolution powder diffractometer, now resolution is very high. It's much better than 0.08%. Highest resolution. Also, they have the 64 detectors. So it can be found that the existence of two phases, the major phases is sodium-based P2 phase, and the minor is the lithium-based O3 phase in the lithium-doped materials. The second conclusion, the lithium ion occupy the vacancies in sodium layer and TM site in TM layer simultaneously in the P2 phase as we expected. Let's see the next page. According to the electrochemical performance test, we can find that the step-like charge discharge profile of a Li-free material has been largely smooth after lithium doping. This is due to the suppressed phase transition of P2 phase to O2 phase. That is 4.1 to 4.2 volts, and ordering process voltage step between 3.1 to 4.0 volts by inactive lithium ion. Let's see this slide. As shown in the left picture, the lithium doped material shows excellent rate capacity, improve a lot compared with the non-doped materials. This material can be charged and discharged at very high current density, up to 20 C. As shown in the right two pictures, lithium doped materials also shows excellent cycling stability after 1500 charge and discharge tests. It still has 73% of original capacity, but for the non-doped material, only 33% of the original capacity remains at the same condition. We believe the excellent performance of the lithium doped material is due to the suppressed phase transition and ordering process. That is my introduction about the first part. We use neutron diffraction, high solution one, and the high intensity one study the sodium-based batteries. But we have three layers. One, we study the these metal layers. We study the sodium layers, and we also study both layers. It's quite promising for the potential materials. Finally, I will spend a very short time to introduce some other techniques. When we use the neutron activation analysis, when we use neutron image. As you may also know that China has a big problem in the last 5 years because of smog problem. So we study this by so-called airborne particulate matter, APM, sample station set up in the suburb of Southwest Beijing. Actually, this is our graduate school near CIAE. PM 2.5, that means diameter less than 2.5 micron. And PM 10, diameter less than 10 micron, were collected on the polycarbonate filter. And with 0.4 micron and 8 micron processed separately twice a week by a gene stacker filter until sampler. The APM samples of both size categories were analyzed for more than 40 elements by instrumental neutron activation analysis. Of leaf-free material have been that's 20. This one. And the project for air pollution analysis based on NNA technology, financially supported by IEA. So we also have the member join this project, and we get huge support from IEA colleagues. We also have the member already joined this IEA organization, focus on this study as experts, which means that we have nearly 30 years of APM sample data. The APM database is also one of the great significance for long-term monitoring of air pollution, and especially for haze control in Beijing. Let's see our result. In order to do source approximate of APM, neutron activation analysis, we used to analyze the chemical composition of samples. 5 major sources have been identified by using positive matrix, the fractionization PMF, including core burning, vehicle exhaust, and waste incineration, construction industry, soil and industry with chlorine. For example, core burning was identified by sulfur and bromine. Secondly, sulfate is from the sulfur exist, while vehicle exhaust and waste incineration was identified by the potassium, zinc, lead, cadmium, and manganese. From this table, you can find the core burning is 29.2%, vehicle exhaust and waste incineration is 26.3%. Construction industry is 23.3%, soil is 15.4%, and the industry with chlorine is 4.9%. We thought it's a fingerprint study, which is very useful, and is qualification and quantity is quite meet that challenge in China for Chinese government. Let's see the next page. Let me introduce about the final part, neutron imaging for fuel cell. The fuel cell technology play a very important role, offering a pollution-free alternative energy supply in contrast to burning fossil fuel. Fuel cells are an applicable technology for mobile and stationary application. You can see from this picture, water management at each cell component like membrane, a catalyst, a gas diffusion layer, and a gas flow channel is one of the key issues in engineering application of the fuel cell. We collaborate with the Tsinghua University, one of the famous university in this country. You can even see this water flow in the fuel cell. Because of the high attention of neutron by liquid water and high transparency of neutron, so fuel cell components, neutron imaging is a powerful water mapping method to visualize the water distribution in operating polymer electrolyte fuel cells and address various issues related to water management. This is a neutron imaging of the cathode nitrogen purging experiment of a fuel cell in CARR. We have done this experiment in the reactor hall. On the left side is original neutron imaging, and on the right is the distribution of water extracted after processing. The dynamic chain of water accumulation in serpentine pipe can be clearly observed. The serpentine means a snake-like pipe. The sensitivity to the thickness of a powder layer can be better than 0.1 millimeter at 100 micron. Let's see the next slide. The fuel cell in-situ neutron imaging device has been developed in collaboration with the Tsinghua University by observing the water transport on gas flow channel and a different current density. In provide an optimization tool to solve the startup failure of fuel cell in low temperature environment. Neutron imaging is proved to be used for the fuel cell development, and we expect more systematic experiment in future. I remember when I visited Batam, we do have the same very powerful facility like HRPD and neutron imaging, and we also work on the neutron activation analysis. We hope in the future we have this kind of collaboration with Indonesian colleagues, and also we build some international competitive facilities on CARR. Here we'll spend about less than 5 minutes to introduce about the CARR. It is a 60 megawatt research reactor, and the flux can reach near to 1.10 to 15. And we majorly use this reactor for neutron scattering, imaging, activation analysis. Currently, we have 13 instrumentation already finished. We are build another 4 to 5 instruments. Finally, we will have 22 instrumentation. If you come to the CARR project, you can see the reactor hall and the guide hall. You can also see we have a lot of collaboration instrumentation and also home built diffractometer. First one, we collaborated with Graduate School of Technical Science, HRPD. Also with Beijing University, we have high intensity powder diffractometer. We collaborate with Uppsala from Sweden part. It's a residual stress diffractometer. We collaborate with Renmin University with 2 elastic spectrometer, so-called triple axis spectrometer. We collaborate with Jülich, German, with triple axis, thermal triple axis. We also work with Jülich colleague. We build a texture measurement diffractometer and also synchronous diffractometer. We work with China Academy of Science. We build 2 triple axis. One is IOP triple axis. We also work with the Chinese Academy of Science, Institute of the Chemistry. We build small angle and also reflectometer. We also homemade the neutron activation analysis spectrometer. Let's see the next page. In this year, we successfully finished the collaboration with Zhongnan University, that is Central South University in China, in Hunan province, successfully built the international competitive diffractometer in the field of engineering. So luckily, we'll finish our thermal neutron imaging and cold neutron imaging. These 2 instruments, we hopefully the next year we can open to the users, both domestic and internationally. That is our instrument on the in the world. It is quite interesting one. We have the long, short, fast, and slow version of the PGNA and the traditional NA. And we also have the neutron activation analysis. That is the in situ measurement of samples. And finally, I will introduce a little bit about international collaboration from European counterpart and our AONSA colleagues and American society. We built up long-term collaboration based on the IAEA support. In the last slide, I would like to mention about our community, so-called Asia-Oceania Neutron Scattering Association. That is Professor Evan Cartney and I work together to push it forward. we have 3 highlights. One highlight, we have the AONSA prize. That is, we give award to our pioneer scientists like Ken Won, like Professor Fuji, Professor John White. They really built up our Asia regional neutron scattering. Secondly, we are discussing about to set up like the Young Carrier Award. That is the new one. My successor, Taku, will focus on this. And some of you may also know some other, we call it the Young Researcher Fellowship. Some of in Indonesia colleague already got its support. We can go to J Park. We can also go to the NBRI. We go to the CARR. We will also go to Australia, and we can also go to the Chinese Relation Source, or even come to our CARR to finish your thesis and do the collaboration work. That is, as a president of the AONSA, I'm very happy working with our colleagues. I'm also proud of this organization. Through this organization, we work with closely with American counterparts, so-called American Neutron Scattering Association and the European Neutron Scattering Association. I would also like to thank our colleagues from Japan, from Korea, from Australia, and especially our Indonesian colleagues. That is my effort to work with our Indonesian colleagues, especially NV Cartney professor. Thank you very much for giving me this opportunity to show all of the progress in China and all of the achievement in AONSA. That's all I want to share with everybody here. Thank you very much. Thank you. That is summary. I will not go to the detail. I hope you can visit our facility in the future. Thank you very much.